So today we're going to look at the Atwoods machine again. So we're revisiting this problem for the third time. And the whole point now is that we're going to look at, well, what happens when our pulleys have mass now and friction. So just to review something from before, consequences of the pulley not having mass and not having friction. So what did that look like? Well, if I have my can here and I had a rope that went around the can, what was true if the pulley didn't have mass and friction, all that was happening here was the string was just moving over the top of the pulley there. It wasn't rotating the pulley and there was no friction between here and here. But now what's going to have happen here is that our pulley is going to rotate. So let's see if I can show this. Okay, so I have a rotating platform here, and hold on a sec. I'm going to put my rope around my rotating platform. So let me put that back down. And it's kind of big, but we can see here the rope on the edge of the platform. And if we do this right, the rope, sorry, this is awkward because I didn't bring a pulley home, but as the rope moves, so does the pulley move, so the rope does not move with respect to the pulley, okay? So that's what's going to be happening here. So the force that exists between the rope and the pulley is, of course, then static friction. And we'll see how that plays in. All right, so here is our pulley. And we're going to hang it from the ceiling by a rope that we're not really going to care about for the most part. And then we're going to have our rope going around our pulley. It's not going to move with respect to our pulley. Let's say that's mass 1. And let's say this is mass 2. And here's our pulley. And if we're looking at the forces acting on this, right, well, I think let's go with the obvious ones here. We're going to have a force of gravity on mass 1, a force of gravity on mass 2. We're going to have a force of gravity on the pulley, which is largely going to be irrelevant, but we should still put it down. We're going to have a tension upwards here, and we'll talk about labels in just a second, and a tension upwards here. Now, if we start talking about what forces are acting on the pulley, we're going to have a tension down here, a tension down here, once again, labels to follow, and a tension going up here. Now, you may ask about the force of static friction between the pulley and the rope itself. And we're not going to draw that in for reasons that are going to become a little bit more clear in the next video when we look at the energy treatment. Just know that these tensions are going to take the place of the static friction acting all around here, as long as the rope does not slip with respect to the pulley. And so that's going to be an important caveat for the problem here. So the rope will not slip with respect to the pulley. And that has a couple of really important implications later on. Now, to review something from before, when the pulley did not have mass and did not have friction, we said that this tension was equal to this tension, and that was simply because of Newton's third law. And this was equal to this, once again, Newton's third law. But when the pulley did not have mass nor friction, these two tensions were equal to each other. That is no longer going to be true. And we'll talk about why in a second. So let's first name these. So this is going to be the tension of the pulley on mass 1. This is going to be the tension of 1 on the pulley. So then this is the pulley on 2 and 2 on the pulley. Now this is just the tension on the pulley, so we can just call it that. We're not really going to care about that. So why is it important that these have different identities? Well, as we saw before, when I actually put the rope on there, this object began to spin. That means that this object started out with a rotational or an angular velocity of 0, and that sometime later had an angular velocity of not 0, meaning it had to undergo an alpha. And what does that mean? Angular acceleration? Well, here's where we introduce a new concept, and that concept is Newton's second law for rotation. If Newton's second law for translational motion was net force equals ma, therefore we're going to see that we can rewrite this for rotation, but here it's net torque, since torques are what cause rotational change. In the place of mass, which is an inertial term, we're going to have the rotational inertia, and then where we had A here, we're going to have alpha. And so their net torque is equal to I alpha is going to be the thing. So therefore, why do these things need to be different? Well, if these were the same, if we were to look at the torque of each of these, right? Well, that would be the R for that particular tension, and that would be the R for that particular tension. These two radii are equal to each other. And if these two forces were equal to each other, this torque, because R cross F, would be equal to this torque, R cross F, but in the opposite directions, meaning the net torque would be 0. So these two things cannot be equal to each other, otherwise this thing would not begin to rotate or change its rotational state. So since we know that this thing does begin to rotate, because if you put the two masses on a pulley and look at it, that's what happens, and when these two are different masses, that must mean that these two forces are different from one another. So therefore we have to label them differently. Okay, so here we go. Let's say a couple of other things about this. Let's say our pulley is a disc of mass M pulley and radius of capital R. Therefore, we know the moment of inertia about the center of mass about the pulley, therefore, is just going to be 1/2 mr squared if this thing is a disc. If it's a hoop, it'd be mr squared. If it's some sort of weird spherical pulley, it would be 2/5 mr squared, whatever it is. So what do we do with all this? Well, the process is largely the same. The first thing we do, as always, is draw the system and draw a full free body diagram for every relevant mass. And we've got this. Mass 1, mass 2, and now the pulley is a relevant mass. So good. Step 2. Yep, step 2 is axes and declarations. So here we go, axes and declarations. I'm still going to use a bent axis because that's going to make a lot of sense for this problem. Okay? So even though we're going to find out that some things that we did before we can't do anymore, we can still use a bent axis for this. So let's say that I say that mass 1 is greater than mass 2, for sake of argument. So let's make this the positive direction. That means this is the positive direction along that bent axis, and then that would make this direction the positive direction sort of around the pulley, and that's going to become super important. So step 1, free body diagram. Step 2, axes and declarations. Step 3, components. Don't have to deal with that here. Everything kind of goes along with the axes. Technically here, if I wanted to do another axis here, perpendicular, I could do that in order to, if I wanted to find out what that force had to be there, we'll do that later. And now what we're going to do is we're going to get to writing sum of forces equations, but here's the trick now. Not only do we have sum of force equations, we're also going to have a sum of torque equation. So how do I know what to do? Well, it's very simple. What we're going to do is we're going to write a sum of torque equation for any mass that may rotate. And we're going to write a sum of forces equation for any mass that may translate. Okay? Now we also might, in each dimension, or each relevant dimension, depending on what the problem is. Okay? And so that just helps us know what we're going to need to write equations for. So here's the thing now. When we approached this problem in the past, we used a systems analysis. Now a systems analysis let us write one equation, sum of force equation, for the whole thing, even though each of them was actually in a normal Cartesian sense moving differently. One was going down, two is going up. But here's the thing. What was the criteria for whether or not you could use that systems analysis? And the systems analysis required all masses move equal distance in equal time. That was the requirement. So here's the thing here. One might move a certain distance down, and two will move that same distance up. But here's the thing. Now that the pulley is a relevant mass, the pulley does not move equal distances. That means we cannot do a systems analysis anytime the pulley has mass and friction because we don't fit the definition of when we can use it. So what does that mean now? That just means that we're going to have a system of equations every single time. So let's look at what equations we can write, and I have to go to a new page to start writing equations. I think we can identify an equation I can write here is a sum of force along the bent axis for 1, a sum of forces along the bent axis for 2, and then we have our pulley here, and we're going to do a sum of torques for that pulley, right? So here we go. Sum of forces along that bent axis, which we'll call the x-axis for object 1, would be mass 1, A1. So that means we have a positive FG1 minus a TP on 1 equals M1A1. Not much I can do there, except I can put in M1G minus TP1 equals M1A1. Okay, good. Sum of forces in that same x direction, that bent axis for 2 is mass 2, A2. And so that had TP on 2 going up, which was in the positive direction for that, minus FG on 2, which is equal to M2A2. All right, and so now I have TP on 2 minus M2G equals M2A2, right? So far here I have 1, 2, 3, 4 unknowns. Wait a second, how come these are not equal to each other? Once again, that was a consequence of this being true. We're going to need a different reason to link A1 and A2, because I think you'll be able to see here that A1 and A2 are going to be the same magnitude, right? But we're going to need a different set of proofs as to why. So next we have to do a sum of torques equation. So if I ask you to write a sum of torques equation, you should stop me and say, I can't do it yet. Why can't I do it yet? If you said, I haven't defined an axis, then you're correct, because that's the critical thing here. Back when we're doing axes and declarations, something else that we need to do is we need to define the rotational axis. Now here that's kind of defined for us because the pulley rotates about its center of mass like that. And over here we kind of made that assumption, but we didn't put it on our diagram. And so a critical step in these problems is going to be to define the axis of rotation so that we can write effective sum of torque equations. So therefore, I can come back over here and I can write a new equation. I'm going to just come down here and say the sum of torques about that axis, that pivot, because in later problems, we might have sum of torques about multiple axes, is going to equal, and this is a sum of torques about that axis for the pulley, is equal to the moment of inertia of that axis for the pulley times alpha. And that's alpha for the pulley. All right, fair enough. So looking back here, we can ask, well, what forces are causing torques? Now, if you remember, a force causes a torque if and only if the line of action of that force does not go through the axis of rotation. And so you can see that FGP goes through the axis of rotation, as does TP. These will not cause torques. These two forces are the only two forces causing torques. So here's how I construct my sum of torque equation. I say, okay, well, this is going to cause a torque, and that would cause this thing to want to spin clockwise or counterclockwise, which is our positive. This would want this to spin clockwise, excuse me, which is negative. So coming over here, I would say we have a positive torque due to 1 on P and a negative torque due to 2 on P, and that's going to equal I. And now I'm going to identify what this is. So I about that axis is I COM for the pulley times alpha for the pulley. Okay, so here we go. Now, torque. Little sidebar, remember, torque here is either equal to, or the magnitude of the torque is RF sine of theta, or we can talk about the magnitude of the torque just equaling the force times the lever arm distance. Now here, that's just the simpler way of doing it, because anytime you have a pulley, the lever arm distance is merely just the radius of the pulley to where that tension acts, because this by definition has to go tangent to the pulley. If you don't believe me, tie a rope around something and try and pull on it and see if you can pull on it in a non-tangent way when this thing is not like physically attached to the object. So how do I do that? What I always do when I'm writing torques is I'm going to put parentheses like that, and now parentheses like that equals parentheses, and then there you go. And now let's fill in the blanks. Because I know this is the force of 1 on P, so I'm just going to write in tension 1P there. Same thing here. This is tension 2 comma P there, right? And then I know that this is ICOM of the pulley. We've already specified that's half mass of the pulley, R of the pulley squared. Okay? Great. Now what am I putting in here? Are those lever arm distances? Well, what are those? That's just very simply the radius of the pulley itself. And now I've constructed my sum of torque equations, my first one. Yay. Okay? Force times lever arm minus force times lever arm equals 1/2 mass P R squared alpha P. Now, if we look at that, how many equations, how many unknowns? Well, 1 unknown, 2 unknowns, same 2 here, 3 unknowns, 4 unknowns, 5 unknowns. Damn it, 3 equations. I need to create another link in order to make this work. And here's where we go back to understanding something about alpha and the objects being rigid objects. So, remember what we said about omega and alpha. What were the most important things about omega and alpha? And if what you remembered was that omega and alpha are the same for all points on a rigid rotating object, then you remember the important thing. So if we think about this here, if I'm talking about the motion of any point on this object, right? The points on the edges, because this is a rigid rotating object, right? If this point on the edge moves a quarter of a circle, this point on the edge moved a quarter of a circle, meaning this point and this point would move through sort of equal distances along that circumference simultaneously. In the same way, that means that this point and this point, because they're equal radii, move at equal tangential speeds, right? Because the tangential speed, to remind you, little reminders over here, of a point in a rigid rotating object is equal to omega times how far it is from the axis of rotation. So 2 points at the same R would have the same VT. And very similarly, folks, the acceleration of those points, if this thing had an alpha, then each of these points is also speeding up. It has a tangential acceleration that would be equal similarly to alpha times R. And this is going to be our key, because if you think about it, coming back down here, the acceleration linearly of this object down, so let's say this object moves down a distance of d, right? Well, where's that coming from? Well, the rope here has to also move through a distance of d, which means this rope here also moves up a distance d. So the tangential speed and tangential acceleration of this point on the rigid rotating object has got to be equal to the tangential acceleration, or the linear acceleration of this one. Meaning going back here, if I call this point like, I don't know, A, and this point B, the acceleration of 1 in the x direction is equal to the acceleration tangentially of point A. Similarly, the acceleration of 2 in the x direction along this is equal to the acceleration of along the tangent of point B. So we can create a relationship then, because therefore, if I know the alpha of the rigid rotating object, I know something about the tangential accelerations of those 2 points A and B. So in this case, I can say that A1 is equal to alpha of the pulley times capital R, because that is how far point A is from the axis of rotation. And A2 is equal to alpha R as well, because they're both at a distance R from the axis of rotation. And in this case, because alpha is the same for all points in the rigid rotating object, and because the two R's are equal, I can therefore say that A1 is equal to A2. So we've proven it in this case that those two objects are going to have the same tangential acceleration, which I'll now just call AT for sake of ease, right? So that's going to be the link that we're going to use in order to solve the problem. So the question now becomes, well, what am I going to try to solve for? Let's say the problem is find the acceleration of object 1. Okay? Because sometimes, depending on what we're being asked for, what happens here is very different. Like if I'm asked to find what the alpha is for the pulley, then I'm going to do a different algebraic process than what I would do before. But if I was asked to find A1, what I want to do is get everything in terms of A1. Well, what changes then? Well, that's going to stay. But this A2 now, because I've proven it, is A1. Well, hold on a second. When would these two accelerations not be equal to each other? That's sort of a weird thing to think about, and we're going to see a problem. It's problem 32 in the textbook later. That's not today, but that's a different day. We're going to come back and look at that. Okay, so what are we going to do here now that we know we have a link between A1, A2, and alpha? Well, unfortunately, what we're going to do is a lot of algebra. We have to plug everything in to solve for A1. And the way we're going to do that in general in these problems is all the linear stuff is going to find its way into the rotation stuff. So what am I going to do? Well, what I want to do is solve these two equations here for the t's, because I don't care about them, to put in here to solve it. So let's do that. T, P on 1, if that comes over to this side, this becomes M1G minus M1A1, excuse me. Over here, T, P on 2 is equal to M2G plus M2. Now, just to show I did a plug in here, A1, because I want to do everything in terms of A1. Now, we're going to plug in here. But before we go too far, let's make our lives a little simpler. Notice in this line, I can eliminate one of the R's because that R also happened to be in here. That makes this problem a little bit easier. Not always true, but certainly true here. So now let's do plugins. M1G minus M1A1 minus M2G plus M2A1 is equal to 1/2 mass of the pulley, R, and in place of alpha of the pulley, remember I'm trying to get A1 in here, I can rearrange this and put A1 over R. Now, a couple of nice things there and a caution. The first nice thing there is notice boom and boom. It looks like the radius of that pulley doesn't make any impact on the problem, which is super weird, but there it is. Second, we're about to do some algebra. Take a look and you tell me what's going to be the most common error people make here. And if you said forgetting to distribute this negative, you're right. That's the kiss of death. It is the most common error in this problem. So let's rearrange, and what we're going to do is I'm going to do that distribution as a separate step because I know I screw that up all the time when I don't do it as a separate step. Okay? Now let's get all the A1 terms onto one side and see what we've got. M1G minus M2G is equal to M1A plus M2A1, actually there's one, plus 1/2 MP A1. So I can solve for A1 then. A1 is equal to M1 minus M2 quantity G all over quantity M1 plus M2 plus 1/2 mass of the pulley. Okay, done. Couple of comments on that result. First, if the pulley has no mass, if this was the normal Atwoods problem, hopefully you will remember that the result that we obtained was just very simply the subtraction of the masses over the sum of the masses times G. So thankfully, this expression here collapses to this expression here if the pulley has no mass and no friction. Yay. So let's look at this. So why can't then we do this just as like a normal systems analysis and then just like deal with the pulley's mass? Well, notice here this 1/2 factor. Well, where did that come from? Well, that came from the notion that the moment of inertia, the inertial related term for rotation, isn't just about the mass, but also about the shape. And that's how that pops up here. And that's going to be generally true in terms of what we have. Because up top, what we do have is a net force term. And the bottom, what we have is not just the linear inertia, but the total inertial term of what's going on. And that's going to be very common in these problems in terms of this structure of answer. So just to review a couple of things, because I know this is getting long. First, I need to understand these two forces are different from each other. Second, we have to be declaring where the axis of rotation is. Third, the systems analysis no longer works because these things don't go equal distance in equal time. Next, we have to remember our links between translational and rotational motion that allow us to put together the links in terms of what we're doing with our system of equations. And finally, just being really careful about our distributions and our algebra because this is a longer algebraic process. So I'm going to have a problem for you to do tonight for yourself and then review. It's a similar type problem to an Atwoods machine, except the geometry looks just a little bit different. Tomorrow, we're going to revisit this problem, but talk a bit in terms of work and energy rather than talking about it in terms of forces and torques.